to get started? All right. All right, today we're going to talk a lot about different ways to turn alcohols into good leaving groups. The hydroxyl into good leaving groups. So a number of different ways. We're going to do a couple different mechanisms here. So really any mechanism that you have seen in class or in discussion is potential mechanism for the midterm coming up. Okay? All right. Okay, so we left off last time talking about secondary and tertiary alkyl halides with the HBr and why it's not necessarily a good reaction for SN2. So we're talking about stereochemistry here. And as you can see, in the first step, we protonate the alcohol right here. Water leaves. As soon as water leaves, we make a carbocation and we lose all our stereochemistry here. This now becomes a planar molecule here. So this carbon, this hydrogen, and this carbon are all in the same plane. And perpendicular to that plane, we have our p orbital. Okay? So perpendicular to that plane. So what happens in the next step is the bromide ion is going to come in and attack. This is a plane right here. So the bromide can come in and attack here. And it can in and attack from the bottom. If it comes in and attacks from the top, you get one enantiomer. If it comes in and attacks from the bottom, you get the other. And it's equally likely to do either side. Okay, so you're going to get racemization, just like we got with SN1. All right, so, yes? It isn't. Really? Sometimes when I open it, it doesn't show up. I'll take care of that as soon as this early afternoon. Okay. Thank you for letting me know. All right, so bromide ion comes in. It can come in from the top here, and it can come in from the bottom. So boom, it'll go here. Or it'll go here. Attack on that side or that side. And so that leads to racemization. So as you can see, when you have stereochemical issues here, you do not want to be making a carbocation if you have a stereocenter, because you're going to lose your stereochemistry. You're going to get racemization. Okay, so let's label this planar intermediate, lose optical purity. Planar intermediate, lose optical purity. All right. So it might not be the best thing to do for secondary. We get rearrangements, and we also have racemization if we have stereocenters involved. So we really want to avoid using HBr with secondary alcohols. So I'm going to give you some other ways that will work better. So we do need alternatives. All right, so there's two reactions, PBr3 pyridine and thionyl chloride pyridine. And we're going to go through both of these, and they work better. You get better yields, and you don't get any carbocations rearrangements. So no carbocation rearrangements here. And that means we're not making carbocation intermediates. If we make carbocation intermediates, we'll get carbocation rearrangements. So in both of these reactions, we don't form carbocation intermediates. So for PBr3 pyridine, that's the most common one. You can also use PCl3 pyridine, PI3 pyridine, but the most common one that we see is PBr3 pyridine. And so what this looks like is, we'll use ethanol here. And we have PBr3. So another possible mechanism for midterm 1. So think about that. For our arrow pushing, our arrow pushing is going to involve the oxygen and one of these bromides, and so I need to make sure that this bromide that I'm going to be involving in this arrow pushing, it has all of its lone pairs. All right, so what's going to happen is we're going to have this oxygen, arrow comes from the lone pair, attacks the phosphorus, and we kick off a bromide leaving group. Now your book does PBr3 without pyridine. I'm going to include pyridine whenever I use PBr3. And what the pyridine does is it's a solvent, and it also can act as a base. And so what it's going to do is in this step right here, it's going to come in and deprotonate that oxygen. So arrow comes from the lone pair on nitrogen, and then we grab the hydrogen and we break the hydrogen-oxygen bond. All right, and then the bromide ion that we kicked off in the first step is going to come in and do backside attack. So we're going to going to grab here, attack this carbon. We're going to break the carbon-oxygen bond. So that gives us ethyl bromide. And so what it's done is we've taken the bad leaving group here, hydroxyl, bad leaving group, and we've turned it into a good leaving group. It's a great leaving group. Bromide's a great leaving group. So we have the same overall process, but we're just doing it a little bit different way. Okay, so thionyl-chloride pyridine is very similar. We're going to be doing a mechanism that's different than the book. Don't use the book mechanism on the test. I still will see people do that, but we're using a different mechanism because the book mechanism is incorrect. And the reason that the book is using this mechanism is that the author has made a determination that this is an easier mechanism for you to learn at this point. And it is a little bit easier, but it isn't the correct mechanism. So I'm teaching you the correct mechanism. I know I've taught a long time, and I know you guys are ready to see the correct mechanism. And by learning this mechanism now, it makes it much easier in 51C when we do many more mechanisms like this. So the mechanism that I want you to see, the one that I want you to use on the test is going to be this one. So this is a possible mechanism for midterm 2. It's one of the ones where I often put this mechanism on midterm. So I'm not promising it will be on the midterm, but I do often put it on the midterm. All right, so let's go through it. We're going to use methanol here. So here's thionyl chloride. We have a double bond to oxygen. We have a chlorine, and sulfur has a lone pair. So I'm going to put lone pairs on oxygen here, and what's going to happen is in the book, they just have the oxygen attack the sulfur and kick off a leaving group, and that's not the correct mechanism. What happens is it's a two-step process to reach that same point. We're going to attack the sulfur, and then we're going to kick electrons up onto oxygen. That mechanism is called an addition. That step is called an addition. All right, and then after that, This is what we have. Well, this is what everything looks like. So certainly different than the PBr3 mechanism. We get an alkoxide here now. We have 2 chlorines. One of those chlorines is going to get kicked off, so I'm going to put lone pairs on the chlorine that I'm kicking off. I'm just going to kick off this one. And we do have a lone pair on sulfur. And so in the second step, the electrons are going to come down from oxygen. We're going to form a double bond. We're going to reform that double bond between the sulfur and the oxygen, and we're going to kick off the leaving group, and that is called an elimination. It's a different type of elimination than we've done so far. What we've done so far is beta elimination. This is an alpha elimination, but it still is an elimination. And then after you do that, we get the same thing that you get in your book, except we've just done it in a 2-step process rather than a 1-step process. So then everything after that point is going to look the same. The pyridine the pyridine acts as a solvent and as a base in this reaction, and the pyridine is going to come in and it's going to deprotonate oxygen. It's going to do the same thing here that it did with PBr3. And that's good because that makes it easier to remember. So we're going to remove this hydrogen here. This is an acid-base reaction. So what we have is a multi-step mechanism, but the steps that you're seeing are, we've certainly already seen the acid-base step many times. Oh, and I got to fix that. Hang on, I need to draw that bond. I'm going to be breaking this bond here, so I'm going to redraw that bond. In my mechanisms, I want any bonds that are breaking to be drawn out. So I'm going to be breaking this carbon-oxygen bond here, so I'm going to draw that bond out. And so what's going to happen is the Cl minus that we took off in the second step is going to come in and do backside attack, kick off the leaving group. So this whole group right here is the leaving group. And then we're going to continue on the top of the next page. We'll finish the mechanism on the top of the next page. So we get Cl, CH3. We also get this oxygen sulfur species. And so the sulfur has lone pairs, the chlorine has lone pairs. And so then in the last step, we're going to this is going to break apart. These electrons are going to come here, make a double bond between the sulfur and the oxygen, and we're going to kick off chloride. So we get sulfur dioxide, which is a component of smog. That's a gas. And so it's going to bubble off the reaction mixture. So that's one of the components of smog that turns it brown, okay? And then we get, and this is going to be important later here, this insoluble salt. So the pyridine works as a solvent. It also deprotonates oxygen. And the other thing it does is it forms a precipitate with any excess chloride that's around. So we get this precipitate. So we form a gas in this reaction, and we form a precipitate, and both of those things act to drive this reaction. So insoluble salt precipitates. All right, so we'll just put a little S here, and then an arrow going down, which means it's just going to fall to the bottom of the flask. Questions on that mechanism? Anybody? Yes? I'm going to talk about that. So I'm going to show you why we don't want to do the mechanism the other way. So this is the way the book does it, so don't do it this way. And so in this mechanism, this is the way the book shows it, and they just have this come in and kick the chloride right off. So they've just accomplished in one step what we took 2 steps to accomplish. So what I'm going to do is I'm going to put a big X through that. Because some people, when they go back and look, they'll copy that and do that on the tests. Okay, so that's not the correct mechanism. Why not? The atom attached to the leaving group is not sp3 hybridized. SN2 reactions only occur on sp3 hybridized atoms. Okay, so we mentioned at the end of chapter 7, which was at the end of last quarter, that we don't get any attack on vinyl halides, for example. Okay, so we don't get this happening, where the nucleophile comes in and kicks off a leaving group on a sp2 carbon. So sp2 bound to leaving group, therefore no SN2. And we also mentioned that you can't do this with a benzene ring also. We don't get substitution. We don't get SN2 or SN1 on a benzene ring. So we don't want to have that either. And so what do these two things have in common? So this can't happen and that can't happen. So let's go ahead and put an X through there. This one here is also an sp2 carbon bound to a leaving group. Therefore, no SN2. So that's what they're doing in the book, is showing this as an SN2. And so we don't get that, and we don't get that. In both of these cases, this carbon is an sp2 carbon. And this is also sp2 carbon here. All right, so that's point number 1. We want to show that as 2 steps. When we have things that are sp2 hybridized, rather than doing direct substitution, we do addition followed by elimination, with the overall effect being the same, but it is a 2-step process. The other thing you don't want to do is deprotonate the alcohol first. So if I ask you this mechanism on the test, and there's probably a good likelihood that I'll do that. That's not a guarantee, but there is a good likelihood. I don't want you to deprotonate. It should match exactly what I've shown you. I don't want you to deprotonate the alcohol first. And I often get this question, why can't the pyridine deprotonate the alcohol first? So let's go through that and show why that is not favored. So the nitrogen comes here, grabs the hydrogen, boom. This is an acid-base reaction, so let's draw out the equilibrium and then see if that reaction is actually favored. Whoops. Okay, so we have RO minus. And then we would have protonated pyridine, which is a pyridinium ion. All right, so for any acid-base reaction, we want to see the direction of equilibrium. We look for the acid on each side of the equation. So let's do that. Okay, so here's our acid here. If we look at the conjugate acid-base pair, that's the one that picked up a proton. Here is our acid here on this side. We look up pKa's. For alcohols, pKa is approximately 15. And for this, this acid here, pKa is about 5. So can you see that the equilibrium is favored in the other direction? So it's this direction here. And if we take a rough difference in pKa's, we can see at equilibrium how much we have of each. And the difference in pKa is 10. So at equilibrium, we have 10 to the 10th to 1. 10 to the 10th protonated alcohol to deprotonated alcohol. So that's why we don't want to deprotonate first. It's not favored. So 10 to the 10th to 1. So, so the answer is, why is this not favored? The answer is the equilibrium is not favored. All right, so we don't want to draw it that way. All right, so pyridine, we use pyridine as a solvent for these reactions because it prevents the buildup of HBr and HCl and is a poor nucleophile. So pyridine, non-nucleophilic. It's a non-nucleophilic base. So that means it's only going to act as a base, it's not going to act as a nucleophile. So that's good because we don't want it acting as a nucleophile. So we're not going to get any of this happening where this acts as a nucleophile. I mean, because you might have been thinking that, okay, well, nitrogen could come and attack the methyl bromide. Once we form it, it can go ahead and do that. And the answer is that's not going to happen because it's a non-nucleophilic base. How do we know it's a non-nucleophilic base? Because I just told you. And we've done a lot of reactions, and it never acts as a nucleophile. So we now categorize it as a non-nucleophilic base. So we don't get any of that thing happening. So we'll put an X through that. So it acts as a base instead. So if we happen to form any HBr in this reaction, it would not allow that to happen because it's going to deprotonate as soon as we form it. So it's going to come and grab that proton, boom. And we're going to get pyridinium ion, and that's kind of a nice reaction because it actually removes the HBr from the solution, so we get the pyridinium ion, and the pyridinium ion tends to precipitate with the halide ion. So in this way, all of the HBr and HCl is removed. HCl, and of course if we used HI, we could use that also, is removed. All right, so why are we worrying about HBr and HCl picking up? And that's because we know that HBr, HCl, or HI, plus an alcohol, gives you RCl or RBr via the reaction we just talked about at the beginning of class, the end of last class and the beginning of this class. The previous reaction. And we know that there's some problems with this, okay? Problems with HCl. HBr and HI. Okay, so where were we? Problems with HCl, HBr, HI that we just talked about at the beginning of class. Racemization, right? Yes. It's not. Oh, turn it on, huh? All right, racemization there. That's much better. Thank you. And carbocation rearrangement. So those are two things that we're trying to avoid by using these other methods. So these methods, by these methods I mean PBr3 pyridine and thionyl chloride pyridine, work well for methyls and primary and secondary alcohols, no tertiary alcohols. Why no tertiary alcohols? Yeah, tertiary alcohols, this is an SN2 reaction in our key step, okay? And so the mechanism is SN2, which means that we can't have tertiary alcohols. And therefore there's no SN2 with tertiary substrates. All right, and the other thing is that there's also no SN1. Oh boy. I'm going to start coughing again. No SN1 either. Because why? What do we need for SN1? Oh no, now you guys are going to start. Because there is no polar protic solvent, right? So we've deliberately chosen a solvent that's not polar protic so that we can't get SN1. Yields are high for these reactions and rearrangements are rare, and that's because we have no carbocations. No carbocations equals no rearrangements. Both reactions are stereospecific. So if we use PBr3 pyridine or thionyl chloride pyridine, we get, well, what do we get? Let's take a look. We did the reaction. Let's scroll back. Let's track it. If this carbon was a stereocenter, it's not, but if it was, let's follow the steps. This first step doesn't involve that carbon, so it stays the same. This step here where we kick off chloride also doesn't involve that carbon, so it stays the same. This step here where we deprotonate doesn't involve the carbon. What happens here? Backside attack, and so therefore inversion. So what you need to know for this reaction is that we get inversion of configuration. All right, so might ask you a question where I want you to draw the product showing stereochemistry. And this is what you would draw. For thionyl chloride pyridine, you get the chloride for PBr3 pyridine, you get the bromide. You can, of course, also use PCl3 or PI3. Both of those will be fine. 100% inversion. Need to know that. And the good news is if you know the mechanism, you'll know what the stereochemical outcome is for the reaction. Advantages over HX reaction and why we even talk about this reaction at all, and that's because we have no rearrangements with secondary substrates. And we also get no racemization. With secondary substrates. Questions, anybody? All right. We have one more method to talk about for converting alcohols into sulfonate esters. And that is to make a tosylate, a sulfonate ester. All right, so here's the process. We take a reagent like this, sulfonyl chloride. The R group can vary. There's a couple of ones we're going to use. I'm only going to use one of them. But this is the reaction here. And so this is our bad leaving group, hydroxyl. We have pyridine also in this reaction. And this is what we isolate. So really similar to the thionyl chloride reaction, but what do we isolate in the thionyl chloride reaction? We isolate the alkyl chloride, and here we don't. We isolate this whole species. So this whole thing is our good leaving group. This whole entire, think of this as a fat leaving group. It's a great leaving group. So in this reaction, we don't convert our alcohol into an alkyl halide. We convert it into a tosylate, or a sulfonate ester. Let's show you the mechanism of this, and then I'm going to leave it to you to think about why we don't get the chloride here. Okay, so let's go through this mechanism. This mechanism is also different than the one in your book. So I want you to use it the way we're showing it right here. So here's our alcohol. And you're going to see a lot of similarities between this mechanism and the thionyl chloride mechanism. All right, so we're going to attack the sulfur. We're going to kick electrons up onto oxygen again. That, of course, is an addition reaction. The two are very similar. We got an extra oxygen going on here, and an R group attached to the sulfur. So that's the difference. And in the second step, the same thing that we did with thionyl chloride is going to happen. Electrons on oxygen are going to come down. And we're going to kick off chloride, just like that. So far it's exactly the same. That's our elimination. Of course, your book did that all in one step, and they just did an SN2. And we know it's not an SN2. Okay, and this is so similar. What's going to happen next? Yeah, deprotonation with pyridine. So pyridine is going to come in. We're going to do protonate. And again, that whole entire thing is a good leaving group. It's not letting me change colors now. So oh yeah, there we go. This whole entire thing right here is our leaving group. And I wrote good leaving group here and great leaving group there. But it's a great. You can change it to great if you want. It's a great leaving group. What's our side product here, which we don't normally worry about, but we're going to think about it here. So what I want you to try to do on your own, I'm going to let you think about this. I'm not going to tell you the reason why. But why is it in this reaction the chloride ion doesn't come in and do backside attack and kick off that leaving group? Why don't we isolate the chloride? Why do we isolate this group instead? Why do we isolate the sulfonate ester? I'm not going to tell you why. I want you to think about it first. So what I recommend is draw out the thionyl-chloride mechanism, draw this right underneath, and see if you can figure out why we get a different product in this reaction. All right, so again here, just like with the thionyl-chloride reaction, don't do it this way. If you do it that way, you're going to actually miss it. So the way that my mechanisms usually work is there are 2 or 3 points each, and each step. And if you combine 2 steps into one, you miss the points for both the steps. So I don't recommend that you do that. So I don't want you to do it this way. Let's put a big X through that. That would go to the same thing, but it is not a one-step process, so I'm not going to show you it as a one-step process. Why is it not a one-step process like this? Because we can't do an SN2 on an atom that is not sp2 hybridized. This atom is not, that sulfur is not sp3 hybridized. So we only get SN2 on an sp3 hybridized atom. Okay, so the question is, so why not sulfur is not sp3 hybridized? So the SN2 can only occur on sp3 hybridized atoms. All right, questions on that reaction? Anybody? Excuse me? So yeah, I'm glad. I was hoping somebody would ask me, how come that is not sp3 hybridized? Because if you use the VSEPR, right, you would see sulfur has 4 groups around it, so it should be sp3 hybridized. But sp3 hybridization can only accommodate, there's like 2 electrons per orbital, right? So that has more than 8 electrons. So, so I think if you go back to GChem, remember when we did this with larger atoms, it would be like D2sp. Well, let's see how many electrons we have. 2, 4, 6, 8, 10. It would be D2sp3 or dsp3, something like that. We don't even deal with d orbitals in this class. Okay, so that's why. All right, so there's many of these. And the good news for you is I'm only using one of them, this one here. This is the only one I will use. So there's many different ones. There's one with the trifluoro analog, and that's actually even a better leaving group. So there's different leaving group abilities. We're not going to worry about that. I think there's a sapling problem where they use the methane sulfonyl chloride. This is the one that I'm going to be using. The para-toluene sulfonyl chloride is the most common. It has an abbreviation, TOS. Cl, or you will also see it as TSCl. So feel free to use that abbreviation if you're using this as a reagent in the synthesis, but you do need to know what it looks like, because I may actually have you draw it out on a test to make sure you know what it looks like. All right, so let's look at some examples. Note the stereochemistry here. So this here is tosyl chloride. We have pyridine. I'm going to draw the product. And then you're going to tell me what the overall stereochemistry is. If I have you draw out the tosyl group, this is what you want your product to look like. So react with tosyl chloride, and our product is called a tosylate. What is the stereochemistry of that reaction? It's retention of configuration here, this carbon. Retention of configuration. That is completely opposite to what you get with PBr3 pyridine and thionyl-chloride in pyridine, right? What do we get with PBr3 and thionyl-chloride in pyridine? Inversion. That's why we need this reaction, because it gives us the opposite stereochemistry. Sometimes we might need to have retention there. All right, so let me give you one more example. I'm going to just use a token mesylate, but again, on the test, I'm going to be using tosyl chloride. This is mesyl chloride. And this ring is drawn a little bit strange, but it's just drawn perpendicular to your page. So this wedge part would be coming out of your page, and you can see that this side here, we're going to have a methyl and a hydrogen. And on this side here, this oxygen is still going to be up. So mesyl chloride is what we would start with, and this would be a mesylate. And again, retention of configuration at this carbon. Retention of configuration. These sulfonate esters can react with a variety of nucleophiles to undergo SN2 reactions. Note the stereochemical outcome of this step. If we take this and react this with a nucleophile, backside attack, right? All the nucleophiles that we talked about in chapter 7, those would be ones that we could use for this. This, of course, is an SN2 reaction, so now we're going to get inversion. And let me draw out our leaving group. The tosylate leaving group. So notice the stereochemical outcome, SN2 attack at a stereocenter, which means inversion. All right, so if we have an alcohol, we use PBr3 pyridine to convert it into a good leaving group. That would be inversion, right? And then if we add a nucleophile, it would be inversion again, so we'd get overall retention. If we use a tosylate instead, we get retention, and then when we add our nucleophile in the second step, we get inversion. So do you see we have the opposite outcome? That's why this is a very useful reaction. And really great, complementary to the other two. We'll stop right there and we'll continue this on Monday. I hope you guys have a great weekend.